So before we close this chapter on a series of groups, we want to do some more results and problems. And the first result we are going to discuss today is Jordan-Holder theorem. Jordan-Holder theorem. The theorem says that any two composition series of a group are isomorphic. Well, when we say this theorem is true for composition series, it's also true for principal series. So we already defined the isomorphism of two subnormal series or normal series. And we know what a composition series is. To prove this result, it's a very powerful result, but it's simple, very easy to prove. To prove this result, we are going to use two earlier results. That is, any two subnormal series have isomorphic refinements. And the second result we are going to prove is a subgroup M of G is maximal if and only if G over M is simple. Maximal means there is no normal subgroup of G, proper normal subgroup of G that contains M, when M itself is a proper subgroup of G. So these are the two results which we are going to use to prove this theorem. So what we do is we'll take two composition series of a group, then we'll see whether we can prove that they are isomorphic. So proof. Let Hi and Kj be two composition series of a group G. When we say composition series, that means this implies Hi over Hi minus 1 and Kj over Kj minus 1 are simple. And that implies from the second result Hi minus 1 is maximal in Hi and Kj minus 1 is maximal in Kj. That means there is no proper subgroup between Hin minus 1 and Hi. No proper normal subgroup. The first result says from 1 Hi and Kj have isomorphic refinements. And that implies but and since Hi and Kj are composition series, because of this result there are no further refinements, because there is no subgroup in between any of the adjacent subgroups here. There are no further refinements for Hi and Kj, and that implies Hi and Kj are isomorphic. The next theorem is this. If a group G has a composition series and N is a proper normal subgroup of G, then there exists a composition series that contains N. This is also very simple. So N is a proper normal subgroup of G. So that means 0 N G is a subnormal series of G. And it's given that G has a composition series. So let Hi be a composition series of G. So this is a subnormal series, this is also a subnormal series, so we have a refinement. So 0, N, G and Hi have isomorphic refinements. So that implies, see, these two have an isomorphic refinements means the refinement of 0 and G is a composition series. And that implies there exists a composition series that contains our next item is a definition. It's a solvable group. Solvable group. a group is solvable if it contains a composition series where all the factor groups are abelian. This is a group which we will use it in field theory when we try to prove the insolvability of a quintic. Okay, the meaning of the meaning of solvable will be more clear when we do that. But try to explain what it means. It's this the word solvable is coming from Galois theory. See, we have a result which states that if C is a commutator subgroup is the commutator subgroup of G, then G over N is abelian if and only if N contains C. So here the group contains a composition series. So if G is the group and Hi is a composition series, is a composition series, then Hi over Hi minus 1 is simple. And it says that this is an abelian group, which means that Hi minus 1 is the commutator group of the subgroup of Hi. That is another way of looking at this. Another way is G is solvable if it can be expressed as a series of abelian groups using extension. That what I mean is, here G is solvable if it contains a composition series where all the factor groups are abelian. So that means, let us assume that Hi is a composition group of G where Hi over Hi minus 1 is abelian. And Hi can be considered as an extension of Hi minus 1. And we can always create a homomorphism from Hi to Hi over Hi minus 1. So these Hi's are considered as abelian group, abelianizing. We are abelianizing these each and every HIs, because this is an abelian group. So we are considering an homomorphism from HI to HI over HI minus 1. So this you can take this as an abelianization of HIs. So that means 0 H1 dash Hn is equal to G. This is a sequence of subgroup, each of which can be abelianized. So that is what I meant. G is solvable if it can be expressed as a series of abelian groups using extensions. This is an extension of this. This is an extension of this, like that. So this is another way of looking at the solvable. The real meaning of solvability will be very clear when we go through the Galois theory. So I don't want to go to the details of solvability right now. Now we'll see a couple of examples on solvable groups. One is solvable and another one is not solvable. S3, the symmetric group on 3 elements, group of permutation on 3 elements, is solvable because we have a composition series here, sigma 0 A3 S3 is a composition series of S3. A3 is the alternating subgroup of S3 which contains even permutations, and we don't have any normal groups in between these two, so this is a composition series, and the factor group A3 over sigma 0 is isomorphic to Z3. A3 contains 3 elements, and S3 over A3 is isomorphic to Z2, and Z2 and Z3 are abelian, and we have a composition series where all the factor groups are abelian, and that implies S3 is solvable. And if you show this result for one composition series, it should be true for all composition series because composition series are isomorphic. So next one is which is not solvable, that is S5 is not solvable. This is a very important result in Galois theory. You will come back to this later. Here the similar we have a similar composition series here, sigma 0 A5 S5 is a composition series of S5 for the same reason, and here A5 over sigma 0 is isomorphic to A5, which is not abelian, and if you show that there is a factor group which is not abelian for a composition series, it is true for every composition series. So that implies S5 is not solvable. This is a very important result. Now let us do a problem. Find all composition series of C60. See, all the composition series are isomorphic, but we still want to find out what are the different composition series that C60 can have. See, if you build a composition series for C60, it should be like this: 0, H1, Hn, and that is equal to 60. And there won't be any normal subgroup between these, any two adjacent subgroups. Since Hi is a subgroup of Z60 for every I, the order of Hi divides 60. And since 0 H1 dash dash Hn is equal to C60 is a composition series, the order of Hi is a prime factor of 60. Because we don't want to see any subgroups in between. So it has to be the order of each of this. If this is a composition, a subgroup in a composition series, then that has the order of that subgroup has to be a prime factor of Hi, actually this is the order of Hi over Hi minus 1 is a prime factor of 60. Not Hi's, Hi over Hi minus 1. So the factors, so we will find out all the prime factors of 60. So 60 is equal to 2 times 2 times 3 times 5. So the order of the factor groups have to be 2, 2, 3 and 5. So the combinations are 2, 2, 3, 5, 2, 2, 5, 3, 2, 3, 2, 5, 2, 3, 5, 2, 2, 5, 2, 3, 2, 5, 3, 2. That is starting with 2. 1, 2, 3, 4, 5. Yeah. Starting with 3, it will be 2, 2, 5, 2, 5, 2, then 5, 2, 2. Starting with 5, it will be 2, 2, 3, 2, 3, 2, 3, 2. So there are 12 different combinations that we can build the composition series. These numbers are the order of the factor groups of the composition series of C60. So corresponding to this combination, of course the composition series will start with 0 and ends with the 60. Okay, so the next subgroup is chosen in such a way that the order of the factor group is 2. Meaning this should contain, H1 should contain 2 elements of the subgroup of C60. The subgroup of C60 are actually 1, 2, dash, dash, dash. These are all subgroups of C60. But the one which contains only 2 elements is 30. So this has got actually the subgroup generated by 30 is equal to 0, 30. 2 elements. And that group over 0 will have 2. So the next element should have 4 elements. So that is actually going to be 15. And the next one should be 3. So that is going to be 5. And the next is going to be this. So this is a composition series of one of the composition series of C60. I'm not going to do everything, but I'll do one more. Let's take this one. So you should start with again 0 and then should end with the C60, and the next subgroup should be chosen in such a way that the order of this factor group should be 3, meaning there should be 20, because this 20 contains 0, 20, 40, 3 elements, and the next should be 10, and the next should be 5. And this is one. So these are the different composition series of C60, and they are all isomorphic. Okay? But they are different. Our next problem is to find out isomorphic refinements. So find isomorphic refinements of the following subnormal series of Z cross Z. The first series is of course the starting subgroup is going to be 0, 0, that is the identity of that. Then we'll have 60C, C. Then we'll have 10C, Z. Then we'll have Z, Z. And this is 1. The second one is 0, 0. Then we have 80C, C. These are all subnormal series. Or subnormal series, but they are not isomorphic. So we need to find out isomorphic refinements of this. So first we'll find out the factor groups of each of these. The factor groups of 1. So this is Z cross Z, because the factor group of 60Z times Z over 0 is this. Then 10Z times C over 60C is going to be just C6, and this one will be Z10. And the factor groups of 2, similarly it's going to be C cross Z, Z8 and Z20. So we need to bring it together, meaning you keep we add So this is actually 4. We need to add Z4 and Z20 to this series and Z6 and Z10 to this series. So adding subgroups to 1 to include Z4 and Z20. So we'll start with the first one. We'll start with the Z times Z. We have to keep these things as it is because it's a refinement. So we should have all these factor groups here also. Then from between these two, you add to include these factor groups. So that is 240Z times Z. Then we have 4800C Z, and we have 0, 0. So similarly, adding Z6 subgroups to 2 to include Z6 and Z10, we'll have this is actually 3. We have Z times Z, then we have 20C because we are going to keep the same thing. Then we have 80C. Then we have to include 6, so that means 480 C. Then we have to have the 10, so that is 4800 C Z, and finally we'll have 0, 0. And this is 4, and 3 is a refinement of 1, 4 is a refinement of 2, and 3 and 4 are isomorphic. These are isomorphic. Now we'll have one more definition. Ascending central series of a group. So let G be any group. So the center of G is defined like this. C of G is equal to elements from G such that it commutes with every other element of G. This is called the center of G, is a normal subgroup of G. So we can consider a factor group. So G over GC is a factor group because C of G is normal. Now let C of G over C of G be the center of G over C of G. The center of the factor group. Okay? So then C of G or C of G is normal in G of C of G. Now we'll take the canonical isomorphism gamma from G to G over C of G. by gamma of G is equal to G plus Z of G. So let this be the canonical homomorphism. And that implies gamma inverse of Z of G over Z of G. This is actually normal in here. So if you take the inverse of this, and that's going to be normal here, is normal in G containing C of G. And let that a normal subgroup be Z1 of G. Continue this process, we get a series of subgroups of G as 0 less than or equal to C of G less than or equal to Z1 of G less than or equal to, or subgroup of, not less than or equal to, subgroup of this. This series is called the ascending central series of we'll do another problem. Let 0 H1 Hn is equal to G be a subnormal series of G with the order of Hi over Hi minus 1 is equal to Si. Then the order of G is equal to S1 dash dash S1 times S2 times dash 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 Sn. We'll do this by induction. So when n is equal to 1, the subnormal series would be 0, and that is equal to H1, H0, H1, and that's equal to G. So what is given here? It's given that H1 over H0, the order of this is S1. But H1 over H0 is nothing but G. Because there are only two subgroups here. So that implies the order of G is equal to S1, implies the result is true for n is equal to 1. Now we'll assume that the result is true for n minus 1. So let 0 H1 dash dash Hn minus 1 is equal to G be a subnormal series of G with the Hi minus 1 is equal to Si. And that implies the order of G is equal to S1 dash Sn minus 1. So we'll add one more subgroup here. So let 0 H1 dash Hn is equal to G be a subnormal series of G with Hi minus 1 is equal to G. This implies Hn over Hn minus 1 is equal to the order of Hn over Hn minus 1 is equal to Sn. Implies Hn is actually G. So Hn equal to G contains Sn cos x of Hn minus 1, order of Hn minus 1 elements. And that implies order of G is equal to Sn times Hn minus 1. And that is equal to Sn times Sn minus 1 dash S1, because we already assumed that this is equal to this. And that is the proof. Our next problem is this. An infinite abelian group cannot have a composition series. For example, if you take Z, this is an infinite abelian group, you cannot have a composition series. Suppose you have a composition series like this, N1Z dash Z, then we can always insert another N2Z, which is greater than N1, and N2 being greater than N1, you can always keep on inserting it. So there is no composition series for Z. So in general, if the group is an infinite abelian, then you cannot have a composition series. So let us assume that Hi is a composition series of G. Well, G is an infinite abelian group. Now, then what happens is there exists a K such that the order of Hk over Hk minus 1 is infinite. Because otherwise using the previous result, G would be a finite group. Now what we'll do is let A different from E belongs to hk over hk minus 1. This is a element different from the identity of this. Then this is an infinite group and A is an element from this infinite group which is different from the identity. Then this is a subgroup of hk over hk minus 1. Now there are two cases. Case 1 is finite. That implies hk over hk minus 1 is not simple. Implies hi cannot be a composition series for G. Second case, A is infinite. That implies A square is another subgroup. Subgroup of hk over hk minus 1, and again implies hk over hk minus 1 is not simple. And again that implies hi cannot be a composition series for G. And that is the proof of the problem. So let us do the last problem of this section. The direct product of the finite direct product of solvable groups is solvable. So let G1 dash Gn be solvable groups. Then we need to show that G is equal to G1 cross dash Gn is solvable. That is what we want to show. So Gi is solvable implies Gi has a composition series, let us say Hij where Hij over Hij minus 1 is abelian. Of course, this is also simple and abelian. Simple and abelian. Simple and abelian. So what we need to do is we need to construct a composition series for G for which the factor groups of adjacent elements are simple and abelian. So build a composition series, let us start with, build a subnormal series as follows and show that it is a composition series where the factor groups are abelian. So we have to start with the identity element. Let EI be the identity of GI. So it has to start with the identity element E1 dash dash En. This is a group. This is our H0. Well, let us take an H00. Okay, and before that I need to explain the composition series of composition series of GI. Okay, it's already there. So we are going to build a subnormal series like this. Next element is going to be H11 times E2 dash dash En. Then H12 times E2 dash dash En. The only difference is the second subscript goes from 1 to 2 dash 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 all the way up to G1, because this is a composition series for G1 times E2 dash dash En. Then again start here, G1 times H21 times E3 dash dash En. G1 times H22 times E3 dash dash En. It goes up to G1 times G2 times E3 dash dash En. And it goes up to G1 times G2 times dash dash G. Clearly, because each GIs are solvable, the factor group of any two adjacent subgroups of G is simple and abelian. If you take anything, let us take in between these two. So actually this goes off. So H12, H11, which is definitely a simple and abelian. And if you take this element and this element, we'll see that H21 over E2 is simple and abelian. So if you go like this, if you take any adjacent two elements, if the factor group of the two elements will be simple and abelian, and that implies G is